No? Welcome back. And the topic today is to try to move over to a slightly smarter way of reformulating a money-body problem. Because we saw yesterday that when we have more than 3-4 particles in a state, then we get lots of contractions to perform. And when we draw the diagrams, we get many of these cross couplings, although it can be pretty simple to set it up, but it becomes tedious. So the question is, can we redefine the vacuum which we have and then see if that allows us to simplify the calculations? Doing that is going to introduce a way to interpret correlations in many-body systems in terms of what is being called particle-hole excitations. And that's a standard way or kind of jargon which allows you to give a physical interpretation to specific physical processes. Reality may not be like that, but this is a kind of way which we use to design or develop models in order to describe the micro physics which we are interested in. So let me switch over to the whiteboard quickly. By the way, you will also find the link to the video of the lectures and also the whiteboard notes. And as soon as we're done today, I will also upload the video, so you will have access to the videos as soon as possible. But I'm going to switch mainly to the whiteboard, and these are notes which I haven't put in a digital format yet, simply because I'm struggling a little bit with finding a proper way of plugging in contractions in MathJax. There is a Wick theorem package in LaTeX, but that doesn't collaborate well with the MathJax for displaying on websites and in Jupyter notebooks. So this is something which I'm trying to sort out. And that's the reason why you will have to suffer my handwritten notes for some time. Okay, so let me quickly remind you of what we did yesterday. So we introduced this kind of graphical or diagrammatic approach to many-body physics. And we had the possibility then to rephrase everything we did algebraically. So diagrammatic diagrams. And typically we would design an operator of the type of a one-body operator. This could typically be written like this. And then we would wait with putting labels on the states. We would have so this would be a one-body operator. We would have a two-body operator, which would look like this, where these dotted lines represent an interaction or some kind of operator which acts on the system. So this is a two-body operator. And this replaces the algebraic expressions which we have been looking at. At the end, you will always have to compute something. So, but the diagrammatic approach is something which allows you to visualize many physical processes in hopefully a way which allows you to develop an intuition about the many-body systems. And then we would define a state, and we looked at a specific state like an alpha 1, alpha 2, and we would define that in terms of some kind of vacuum state. In our case, this is the true vacuum. And then we would write lines here, but we would not put arrows, but we would put labels to indicate that these are two states. So we have created two particles in state alpha 1 and alpha 2. And then when we computed the contractions, and we had, let's say, a two-body operator, or phi 0, of an HI of phi 0, and the case which we looked at yesterday was exactly this case here, a two-body state of a one-body operator, alpha 1, alpha 2 here. And the way we would display that was in a pretty simple way. So let me just, if you have had time to write down, I'm just going to switch slide here. So the way you would write it down would be in terms of this drawing here, which represents the bra state. So this would be alpha 1, alpha 2 here. This is our alpha 1, alpha 2 state. And then we have the operator. This is the two-body operator. And then the contractions are represented by us hooking together these different lines. And then we have the initial state, which we begin with, alpha 1, alpha 2 here. And then we would have the two outgoing states, or the states we have created, alpha 1, alpha 2 here, and they get contracted here. And every time we perform a contraction, we put an arrow to indicate that we have contracted two lines, which means in this specific case that we have taken the operator. In this case here, we would have from this side, there would be an A delta and an A gamma acting on an A alpha 1 dagger and an A alpha 2. And then this is contracted with that one. So we had a gamma here and we had a delta. And then we have an alpha here. This is just the operator. And then we had this contraction here. So at the end, when we looked at the possible contractions, this gave us a matrix element or an integral, which was given by this expression here. So that would be that specific contraction. And we would write that one with the left state in the brass side as an outgoing left state here. So we will put a label alpha 1. We have the operator here. So when you see arrows, that means that we have calculated some expectation value or some contraction actually. This is the arrow means that we have contracted the creation and annihilation operators. And then we had an alpha 1 and an alpha 2 here. So that was that specific contribution. And then we could cross the lines alpha 1 and alpha 2 here. So we would get the exchange term. And then we could continue along these lines. We would get two more contributions. But one of the contributions is identical to this one. And the other would be identical to the exchange term. And then we recover exactly what we would have if we calculated everything in algebraically, as we've done before. So it's a very compact way of writing down the different contractions. Now, the problem which we face is as soon as we get, we have many single particle states or many particles, this is going to become pretty cumbersome. And that begs for us introducing a different formalism or redefining the vacuum, as you will see. And that's going to give us a much more compact way of calculating expectation values. But what I wanted to do is actually to go through one of the exercises which we have today. And in the exercises, you're asked to calculate the expectation value of ground state to ground state transition with this Lipkin Hamiltonian. And in that case, we had 4 particles in 4 different single particle states. And this is already a case where we have to look at many different types of permutations of the, or not permutations, that's the wrong word. It's actually pairs of particles which are acted on by the two-body interaction, and then single particles which are acted on by the one-body operator. So let's look at that as an example. And let's now just write it down here. So the example is this Lipkin model. Or we could actually write this in terms of any two-body interaction. We don't need to be confined to this Lipkin model. So what we have in that specific case are 2 states with a spin up and spin down. So this could be a spin down state, and this is a spin up state. So these are fermions. And then in our particular case, we have 4 particles. If we assume that this state is the lowest lying state, then each one of these has specific slots which could point to additional quantum numbers, which we don't define yet. And then you would have new slots here, which are now, so when I'm marking it like this, it means that the particles are occupying these slots. And up here, we would have 4 more possibilities for the 4 particles which we have. So we have n equal to 4. And here we would have the slots 5, 6, 7, and 8. So this is the model. And if you want to codify this one, you would have 8 single particle states. Half of them have the same spin projection, and the other half has the other spin projection. But then the numbers 1, 2, 3, 4, which we could label with a quantity p, could be some other quantum numbers, which we don't need to specify. So p equals 5 and 6. And then we are making an ansatz for the ground state, where we now assume that all the particles are in the lowest lying state. This is an ansatz. It's not, when you add the interaction, this is not the true eigenstate for the ground state. But the eigenstate for the ground state will be a linear combination of these different Slater determinants. So in our case, this would be something like an A1 dagger, A2 when we represent it in second quantization, and this is an A4 dagger acting on 0. And we would often write this one as a 1, 2, 3, 4. This is another way to write this state here. And what we're going to do now is simply to look at all the possible contractions which we can make when we have a two-body operator. So we take just a general two-body operator, and we don't specify it to be exactly equal to the one you have in the exercise. But we're now just going to look at the possible types of contractions which we can have. And just keep in mind that this is a two-body operator. So this means that we will have a chain. When we take this expectation value, we will then have a chain of operator which looks like this: A3, A1, A2, A1. And then we have the operator. I'm skipping the sums over the different states which we have in the operator. And then we have this A1 dagger, A2, A3 dagger, and A4. Now, the thing now is that this operator acts on two particles at a time. So it could act on 1, 2. It could act on 1, 3. It could act on 1, 4. Act on 2, 3, 2, 4, and 3, 4. So we have 6 possible combinations. Does that sound reasonable? So the type of pairs which we have here, since these are the same states, this means that we would have 1, 2 interacting. We could have 1, 3 interacting. We could have 1, 4 interacting. And then we would have 2, 3. So the interaction picks 2 particles at a time. And then we would have 2, 4. And the final one would be 3, 4. So these are the sets of pairs of two particle states which are acted on by the interaction. Now, this state which we have here on the Bryan-Niquette's side, being the same states, it means that in this case here, we would have then the states 3, if we now let 1 and 2 interact, then 3 and 4 have to match each other. So 3, the creation operator in 3 here, cannot be coupled with the creation operator, no, the annihilation operator in 4 when we take the contractions, because these are different states. So when we look at this specific contraction, suppose now we take the 1, 2 case, and you will quickly see the pattern here. So if you want to automatize this, you would then pick all the specific combinations which you can make, the pairs 1, 2, 1, 3, 1, 4, and then you would simply calculate these specific matrix elements, and then all the other states will be called so-called passive bystanding states, which just give rise to Kronecker deltas, and these Kronecker deltas are quantities which we normally leave out. But let's go through the contraction for one of these cases. And then you will see immediately the pattern for the other ones. So we have A2, A1, and then we have A alpha, A beta, and then A delta, A gamma, and then we have A1 dagger, A2 dagger, A3 dagger, and A4. So I'm skipping all the other quantities like the vacuum state, the matrix element. We are simply looking at the contractions. And now we are going to look at the case with 1, 2 here. So that means that one thing which we could have would be this contraction. And keep in mind now that we are using Wick's generalized theorem. So it's only contractions between chains of normal ordered sets of operators. So we can have this one, and then we can have this one. That's one possibility. And then we can have this one and that one. This is a term which we calculated earlier. If you now remember back to last week, then we had a case where we didn't have these two guys. We didn't have these ones. And we simply looked at the possible contractions which you had with a two-particle state with a two-body operator. So when we do this, we are going to get back the same expression, except that now we have to be a little bit careful, because here we have two particles, bystanding particles, and they can only contract with themselves. I cannot have a 3 going to 4 because they are different states. So else that would give 0. So if I look at that specific contribution, I'm going to get a delta gamma of alpha 1. I'm going to get a delta alpha of not alpha 1, but 1. Because so I have a gamma 1, and then I have alpha 1, and then I have a delta of 2, and a delta of beta of 2, and then I have a delta 3, 3, and then a delta 4, 4. Now, what is pretty common now is to skip these Kronecker deltas in the final expression. But you should keep in mind that they are there, but we simply suppress them when we are setting up the final result, because these just give ones. So this leads a matrix element, which now would be given by 1, 2, and V, and 1, 2, as we found previously, and multiplied with these Kronecker deltas. So what it means when you now are plotting this diagrammatically is that you have these states, the alpha 1. So we have 1, 2, 3, and 4. And then we have the interaction here. And this has a gamma of delta, alpha, beta. And then we have the final state, which is the same as the incoming state. And then we would have 1, 2, 3, and 4. So diagrammatically, it means that we contract this with that one, this with this one, and then we perform this contraction, and this contraction here. But when we now want to simplify things, we leave always out the Kronecker deltas. So if you look at these expressions which we have, I'm not going to repeat what we did last week, but we get 3 more sets of contractions. And then we summarize everything with a factor of half in front of the operator. Then we end up the final result for 1, 2 is going to be given by 1, 2 of V, 1, 2 minus, and then we have the exchange part. And this is something which we calculated last week. And I'm dropping the Kronecker deltas just in order to simplify the notations here. So that's what we would get. And we would typically write this in terms of an anti-symmetrized matrix element. So this is pretty common to actually write it like that. So diagrammatically, this means that what we get now is the following. So if we now set up the diagrams, we are going to have the following diagrammatically. So there's going to be the direct term. So we have the direct term here with 1 and 2. And then we have 1 and 2 coming in. And then we have plus, but then we have this exchange term. We keep these fixed, but then we have interchanged them. So this gives rise to a minus sign when we now want to write out the algebraic expression. So we have a 1 and 2 here, we put arrows. And this is then multiplied with the contractions we made with the states which don't interact. So we get a 3, and then we have a 4 here. But it's common to skip the last 2 ones. And then we just keep the interacting part. This is sometimes rewritten, this guy here. In these diagrams are called normally Feynman goldstone diagrams in non-relativistic money-body theory. Or some people just call them Feynman diagrams. Then there is a more compact way of representing this, because we can rewrite these two here in terms of the direct term and the exchange term. So let me just remind you that we call this the direct term. And then we have the exchange, because we exchange a pair of particles. It's common to rewrite that one in terms of another type of diagram, which is called a Hugenholz diagram. So a Hugenholz diagram would be something which we would write like this. And that assumes that we have actually defined this anti-symmetrized matrix element, which you see here. So if we use that one instead of the two individual components, the direct and the exchange, this diagram is often written like this. So we would have 1 and 2 here, and 1 and 2 here. So just note that when I put arrows and labels on the different legs, that means that I've actually performed the calculation of an expectation value. Okay? If I don't put labels and arrows, it means that this just stands for a specific operator, and then we have to perform operations on specific states, and then eventually at the end we would calculate expectation values or transition probabilities, depending on what we are doing. So these are just notations which you will encounter in this course and also in any text on money-body physics. And it's common to, in a way, compactify these two terms into this one. So if you see this notation, that means that we have, when we are now going to calculate it, so when you take this one, when we now use the diagram rules, what we would have then is that on the outgoing side, we have to the left 1 and to the right 2. We have an interaction which we haven't defined. It could be an operator, two-body operator. We could just write this in a generic way as a two-body operator. And then this will be the same as 1, 2, and then it is an anti-symmetrized matrix element. So when you then want to do actual calculations, you're not going to calculate with diagrams, but you're actually going to calculate with algebraic expressions, and then you need an expression for this quantity. And this is what you read directly off from the diagrammatic representation. So you can discuss physics now as stating that we have an incoming state 1, 2, there is some kind of interaction, and then we end with an outgoing state 1, 2. But actually what we had was a state with 1, 2, 3, 4. So you would have to describe from the context what happens to the other particles. Now, the thing which is interesting for us now is that if I now go to the next case, if I take 1, 3, we will have the same case as in the previous case, except that now we are going to connect these operators from the interaction with particle 1 and particle 3 instead of particle 2. And it shouldn't come as a surprise that what we are going to get then is simply 1, 3, V 1, 3. And then if I take the exchange term, it's going to be 1, 3 of V 3, 1. And then we are going to have a Kronecker delta 2, 2 and a Kronecker delta 4, 4. Okay. Then if we do the next one, 1, 4, what we are going to get then is simply 1, 4, V 1, 4 minus, and then I have 1, 4 of V 4, 1. And this is again given by a new Kronecker delta between 2, 2 multiplied with delta 3, 3. And now you start seeing a pattern here, because the total contribution to the ground state expectation value contains all these pieces. So I could have a 2, 3 here, which is the next case. And then again, it shouldn't come as a surprise. We will get a 2, 3, a 2, 3 here minus. And then we have a 2, 3 of V of 3, 2. And this is multiplied with delta 1, 1 and delta 4, 4. And then we have a similar one for 2 and 4. And I'm not going to write them because it's pretty obvious what they should be. And this is a 3, 4 here. So if I now skip the Kronecker deltas, then I can sum up all these contributions. And when I sum them up, you see now that if I set up the final sum here, then I have an h of I of phi 0. So we are going from the same Slater determinant to the same Slater determinant. And in our specific case, this is going to be a sum over I and a sum over j from 1 to 4 and 1 to 4, with the restriction that I is less than j. So we're actually making a restriction. So in principle, we sum I less than j. And the expression is going to be given by ij of v of ij. And now I'm simply writing this in terms of the anti-symmetrized matrix element, just to simplify life a little bit. Diagrammatically, you would simply write this if you, and this is a way which we are going to make more compact when we introduce holes and particles. But what you would write it like would be something like this. So you have I and j, and then you have I and j here. So if these are states below the Fermi level, when we introduce this particle hole formalism, this diagram is going to look slightly different. It's actually going to look like this, because then we, if holes, so if I and j are below the Fermi level, so F for the Fermi level, then we are going to rewrite this one in the following way. We have an I here, and then since we are using this notation here, it's going to look like this. And then we have a state j. So the summation is then replaced by a diagrammatic representation. But I'm coming back to this. I'm just anticipating a compact way of writing the double sum and the specific contributions of every element in terms of just two loops. So, and when you see this one, this is going to be a vacuum to vacuum expectation value of a two-body operator. And then you can repeat the same with the other guys. Now, the thing which is interesting for us now, however, is that if we are getting into many more particles, this becomes quickly a little bit cumbersome. So this kind of notation which you see here is going to make things much more compact and easier to deal with when we have many particles. Now, one thing which I wanted to mention here for you is this, that this is an instance, and I wanted to show you another example, which is also relevant for later when we are going to use this Lipkin model. So this is an instance of the Condon-Slater rule. Which we had as an exercise in the previous week. And in that specific case, we looked at the expectation values or the transition operations when we went from the same state to the same state, or when we went from one Slater determinant to a new Slater determinant, which differed by one single particle state. And then we had the case when we went from one state to another state, which could differ by two single particle states. So we can actually recalculate this using second quantization. So let's have that as a kind of a small digression before we move on to the introduction of the particle hole formalism. So let's look at the case where we now calculate a Slater determinant phi 1 and hi and phi 0. Well, now the difference is that phi 1 is a Slater determinant which differs by one single particle state. And here we can actually calculate things in a much easier way than we did when we did everything in what's normally called first quantization, as we did it in that specific exercise. So let's take a look at that. So we are going to define this state phi 1. This is going to be given by A1 as before, A2, A3, but now instead of A5, we have A4, we have A5. And then we stick to phi 0, so which is A1, A2 dagger, A3, and A4. So what it means is that if I look at this phi1, this newcomer, this is going to look like this. So we have a state here in slot 5. And then we have a 1, 2, 3. And then we have a vacancy here. So when I have a circle which is not filled, that is the same as me having knocked out a particle from that state. So the interaction now is going to create a state where I've knocked up one of these single particle states in an excited state. This is something which we later are going to call a one particle, one hole excitation. So we are going to make a definition of states above the Fermi level as particle states and states below the Fermi level as hole states, because when I knock out one, I leave a hole. This is why we use this notation of a hole state. So this would be a state which is now knocked out, a particle knocked out from state 4 into state 5. We are going to come back to this after the break. But now we are simply going to make the calculations. So what we have now is the following. So we would have an A5, A3, A2, and A1. And then we have A alpha, A beta, A delta, A gamma, A1 dagger, A2 dagger, A3 dagger, and A4. So let's now take a look, when you look at the contractions now, and what you will see now with Wick's theorem and second quantizations, what you did in that exercise with first quantization for the Condon-Slater rules is that you actually had to calculate, set up the determinants, and run through the calculation of the different integrals. If you now look at this case here, and we let the interaction act on 1 and 2, and then we see that 1 and 2 is going over to 1 and 2. So what would you expect from this case if you now set up the contractions?
It's 0.
It's 0, exactly, because the 3 is obviously going to 3. But then we have 5, which goes to 4. And that gives us a Kronecker delta, delta 4, 5, which is 0. So we can just write 0 here. And now we can repeat the same thing. And if I now do 1, 3, going to 1, 3, so it's acting on particle 1 and particle 3. And we know that particle 1 is obviously in this state 1, and particle 3 is in this state 3. What would we expect from that one? If you now look at the contractions. Any good suggestions? So I'm going, so 1, 3, 1, 3 means that I have, if we now just mark it like this, we would have this one going to one of these. We would have this one, which would go to that. And then we could have this one going to that one, and this one going there. It's 0 again, because we still have delta 4 and delta 5, and Kronecker delta 4 and 5. So that has also to be 0. If I now take, on the other hand, if I take 1, 4 going to 1, 4, would I get 0 then? So if I take the final case here for particle 1, so I'm now looking at these two guys here, this one, and this one being selected by the interaction. This is particle 1. And then I'm going to 1 back here again. But then I'm going to 5 here, which is where we have placed particle number 4. Would that be 0? No, because then the interaction would actually act on particle 4. So what I would get then, if I now just use the rules which I had, this would simply give me 1, 5, and V, and then 5, 1, 5, 1, 4, minus 1, 5 of V, 4, 1, when I do the contractions. That will be the total number of contributions which I'm getting. And now you can see that there is a specific pattern here, and let us do that before we take a break here. So we have A5, A3, A2, A1, and then A alpha, A beta, A delta, A gamma, A1, A2. So we have the case with 2 free, going over to 2 free. And that's also 0, because we are then left with the Kronecker delta with 4 and 5, which is 0. So this gives us also 0. But I can have a case where I now have 2 4 going over to 2 5 here. And that is non-zero. So this term would give us now 2 and 4, now 2 and 5 of V 2 and 4 minus 2 and 5. Right in here. 2 and 2, 5. And V of 4, 2. And then I have the final term when I now take the transition 3, 4 to 3, 5. And that is also non-zero. So that's the final term. And that would give us 3, 5 of V 3, 4 minus, and then I have 3, 5 of V of 4, 3. So you can now see that there is a pattern here. So what we could do now is to assume that we replace the states, replace 4 and 5 with a generic label, with the labels K and L, totally generic labels. That means that the other states is something which I would label as I. So that means that the contribution here to this specific expectation value is going to give us, when we sum up everything here, is going to give us exactly what we had with the Condon-Slater rule when we had the difference between one single particle state in the 2 Slater determinants. So this is now going to give us a sum over I, and I has to be different from K and L. So these 2 states are fixed now, these states 4 and 5. These are the states which change. So that means that I would get a matrix element IK. So this is, this should be L, which is 5, I of L, and then I have V, and then I have I of K. And this is anti-symmetrized. And if you now see I changed the 4 and 5 with K and L, you see that all these matrix elements, they contain the sum 3, 2, and 1. And then I have the state K here, which would be the one here, which I call 4. And you see that you have it here, you have it here, and you have it all in all the expressions. And then finally, you have the state L, which is state 5, which you also have in all the expressions here, here, and in the previous case. So I can actually calculate this case with the Condon-Slater rule in a much easier way than I did when I set up everything in first quantization. Now, finally then, the last term which we have is the case when the Slater determinants, so I'm going to define a new Slater determinant, and this could be a determinant which goes like A1 dagger, A2 dagger, and then I have A5 dagger and A6. And then I have my phi 0 as before. This means that the state phi 2, which we have here, would be something like this. So I have the slot 5 here and the slot 6. And then I have the slots 1 and 2 here, which are occupied. But then I have a vacancy in 3 and 4. So my state 3 is moving over there. Sorry, this should be a 4. And then this is promoted up here. So this is now a new state, which in the language of particle hole excitations is something we are going to call a 2-particle 2-hole excitation. And when I now calculate this specific expectation value, phi2 of hi of phi 0, and I'm just going to leave that as a small exercise to you guys. This is going to be given by the expectation value of 5, 6 actually. So these are the states we end up with. So the only possibility is actually 5, 6, and V of 3, 4, anti-symmetrized. And this is obviously multiplied with the Kronecker deltas with 1, 1 and 2, 2. And this is the final term in the Condon-Slater rule as long as you have a two-body interaction. If you have Slater determinants which differ with more than 2 particles, then this expectation value is exactly equal to 0. So this is a very efficient way of setting up the calculation of the Condon-Slater rules. So in general, this means that if we now have in a general case, so we have 2 different single particle states, different states, we can now write a Slater determinant phi, which we label with K and L. And then we have, so these are the states which now are different. And then we have I and J. So we start with the states I and J, and these change to K and L, like we had with the 3 and 4, which changed to 5 and 6. Then we can write this matrix element in a more general term. That means that if we now look at the expectation value, and we look at the K and L case, so these are the only, it's a way to indicate that they have 2 single particle states which differ in a Slater determinant, I and J. This is simply going to be given by the anti-symmetrized matrix element with the states K and L on the brass side and I and J on the ket side. So that's a pretty compact way of setting up this kind of notation. Now, everything which we've done here is going to serve as a kind of warm-up for the particle Hall formalism. And you see now that if you have a Slater determinant with hundreds of particles, this is going to be pretty, how to say, not nice to calculate with. In particular, since the interactions are at most, in most physics applications, you have at most 2 to 3 particle interactions. That means that it will act either on pairs or sets of 3 particles at the same time. That means that all the other guys are not participating. So that means that what you need to do then is simply to set up all the possible groups of the permutations, like the 1, 2, which we had here, the 3, 4, 1, 3, etc., etc. So can we simplify this? So since I'm asking the question, the answer should be yes. And what we're going to look at after the break is this particle Hall formalism. So let me just write it like this here, particle Hall to simplify. Formalism to simplify calculations. And this is essentially done because we have a Fermi level, which we can define, and we have at most 2 to 3 body interactions. So we are never going to act on all 100 particles if we have 100 particles at the same time. So the first lecture today was more in a way to motivate for what is coming. We can still, with 4 or 5 particles, we can run through things by hand, as you saw, as I did now. But we are going to simplify things now. And you will find this a much more compact formalism. And this is the one which is typically used in basically all of many-body physics for fermions. When we deal with bosons, then the things change, because for fermions, you can only occupy 1 single particle state at a time, as long as a single particle picture is meaningful. Okay. Should we take a small break? Any questions? Okay, so after the break, we start with the particle Hall formalism. I'm just going to stop the recording. So when we look at the particle Hall formalism, what we need to do now is just to make a simple drawing first. And the kind of drawing we're going to look at is a drawing for a state. So we assume now that this phi 0 contains now n particles. That means that we are going to have A1 dagger, A2, A3 dagger, and up to some A of n, like this. This is the state, and n can be a huge number. If you're dealing with electron gas, which is an idealized system, which is widely used in solid state physics, this is, n is actually infinity. You have an infinite number of electrons. Now, what we are going to do here now is to redefine things a little bit. So let's just make a drawing here. So if we now set up these different states, we would have now states up to the Fermi level. So we're assuming that all these single particle states are occupied. So this is 1, 2, 3, and then we have n minus 1, and then n. And sometimes we are going to label this n as just f, just to indicate that this is the last single particle state, which then defines the Fermi level. And typically you would then fill up all these states, and this defines your phi 0. So that Slater determinant is now given by filling up all the single particle states up to the Fermi level. And then this just continues above here. And in principle, so this will be n plus 1, n plus 2, n plus 3, etc. In principle, this goes up to infinity. But normally we would put a cutoff, which we call d, or n. So n is the number of single particle states which we now use to define an effective Hilbert space. So in principle, we should have an infinity of states. Most of the basis functions you end up using, the computational basis states, like a harmonic oscillator, they have an infinity of states. But we cannot deal with infinities. So these n states are those which define our system. And if I now define a new Slater determinant, so if I have an A n dagger plus 1, acting on this state, 1, 2, 3, up to n, then what I have to do, since I have a specific hierarchy for these states, I need to rewrite it in terms of n permutations of the creation operators, so that I end up with a new determinant, which is 1, 2, 3, up to n, and then n plus 1. Because I have decided to have a hierarchy of states. So 1 comes before 2, 2 before 3, etc., etc. And then I want everything to be in this kind of ordered way, which we also call the Hartree state in the beginning of the semester. And however, this is now an n plus 1 state. What you had here is just an n state, n particle state. So just keep that in mind when we are now looking at these specific operations. And then if I have a of alpha acting on this 1, 2, 3, up to n, then I have to be careful, because if alpha is not contained in this state, then this is automatically 0, because then we are trying to delete something which doesn't exist. So that means that alpha, we have to make the assumption now that alpha is contained in this set of single particle states 1, 2, 3, up to n. So that means that alpha is one of these specific states. And let's now look at an example here. So what we would have then is that we have an A alpha acting on 1, 2, 3, and then we have alpha minus 1, and then we have alpha, and then we have alpha of minus 1, and then alpha plus 1, and this goes all the way up to n. And in this specific case, we now have to make the alpha minus 1 interchanges. So we end up with a new state when we have ordered everything, which has minus alpha minus 1 interchanges. So alpha is just one of these numbers from 1 to n. And then we have 1, 2, 3, and then we have alpha minus 1, and then we have alpha plus 1, and this goes all the way up to n. And this is an n-1 particle state. So we're going to also introduce some notations here. I'm going to use this notation phi 0, but sometimes you will also see me using a notation C, and I have to be careful so it doesn't look like a 0. So C stands for core. So you would have a core state, and this is now, when we look at it, it's given by this product of I equal 1 up to n of A of I dagger acting on 0. So this is going to be the ansatz for the ground state of the system. And in a typical fermionic system, we assume now that this ansatz, which is not the true eigenstate, but it's normally an eigenstate of the single particle operator. So when I have H0 acting on phi 0, this will give me an energy which I'm going to label E0, acting on phi 0. So this state phi 0 is normally assumed to be an eigenstate of a part of the Hamiltonian. And that defines our computational basis. And you remember now that this epsilon 0 would then be a sum from I equal 1 up to n of these epsilon i's. And we normally call this a reference energy, because this phi 0 is often called a reference state. But we are coming back to this one. Now, another type of notation which you will see is that we will write this phi 0, and this is pretty common in many textbooks, is that this I is less than equal than F, which is the Fermi level. So when you see this F here, that means simply that we are including all states up to the Fermi level. So these are just notations which I will use interchangeably. But this is the compact notation for the system which we have. So that means that if we act on this specific state, and that single particle state is not included, we know that this is non-zero, is 0. So if I act with a state A alpha on this Slater determinant, we know that this is 0 if this alpha is not included in this set 1, 2, 3, up to n. And sometimes I replace n with F, or F, just to say that this is a Fermi level. And then if I have A alpha, so if, and then we have else, A alpha acting on phi 0, this will be different from 0, because then it's included. But we have seen this before. So what we're going to do now is a little bit strange, but we are following a historical path. And what we're going to do now is to introduce a new creation and a new annihilation operator. And these are being called quasi-particle operators. So this is going to be an intermediate step, because at the end, we are going back to the operators A dagger and A. But we define now a new operator. And this operator is now going to be an operator which, when it acts, so we define this operator B of alpha and B of alpha dagger. So alpha, B of alpha is the Hermitian conjugate of B of alpha dagger. So this is a creation of, one is a creation operator and the other is an annihilation operator. They are going to have the same commutation rules as what we saw previously. B alpha dagger, B beta. And this is equal to 0. And also, when I take the contraction, the only contraction which is non-zero is this one. So this is going to be equal to delta alpha beta. And then if I try to take the contraction here, then this is going to be 0, as before. So I want to have the same calculational rules as before. And now I'm going to define an operators in the following way. So these operators will be defined as, or did you get time to write it? All fine? Or I'm writing too fast. Okay, so these operators are now going to be defined in the following way. So when I act on with this B alpha dagger on this vacuum state, or this reference state, as we've called it, this is going to be equal to the action of A alpha on the same state, phi 0. And this is something which we write as new state, where I just put this alpha when alpha is larger than the Fermi level. So that means that alpha is what I will call a particle state. So we are going to label the states which you see here, the states above the Fermi level, as particle states. And we are going to label this one as whole states. So if it's above the Fermi level, then what we are doing now is that we are adding a particle. So just to be more precise here, when I do this on phi 0, this is going to be given by alpha, and then I have 1, 2, 3, up to n. And then I can obviously reorder it so that it actually fills in the spot which I want. And in this particular case, this is going to be given by minus power of n, and then I have 1, 2, 3, n, and then comes this alpha, because alpha is above the Fermi level, which means that it's above the state n in my hierarchy. Then I have the following. If this is below the Fermi level, so these are just redefinitions of the operators. So if this acts on this phi 0, I'm going to write this one as an alpha 1 minus, which simply means that I'm taking out a state. And this is if alpha is smaller or equal than f. And you can see that because if I alpha is acting on this phi 0, this is the same as A alpha. And then I have an A1 dagger, and I have an A2 dagger. And in here, there is an A alpha dagger. And this goes up all the way up to alpha of n. So since this state is in there, that means that this contraction is now going to take away a particle in the state. So this is an n-1 state. So this is the definition of that specific operator, which we have introduced now. And then I'm going to set up a new operator. And so we can simplify this, and we just write it like a B of alpha dagger, which is equal to A alpha dagger if alpha is larger than the Fermi level, and A alpha if this alpha is less than the Fermi level. Now, what we are saying now is the following. If it's above the Fermi level, we create a particle in a particle state. If it's below the Fermi level, we create a hole below the Fermi level. So you create a particle above the Fermi level, or you create a vacancy or hole state below the Fermi level. And that's why you put this creation symbol on the operator B. So you create a hole or you create a particle. And now particles are states above the Fermi level. Or just sloppily speaking, when I say particles, it means a particle state above the Fermi level. So this is just a new redefinition of a particle state compared with a true vacuum. And the benefit is now that we are going to run calculations where we don't need to deal with all the states which fill up the vacuums, the new vacuum state. So this B of alpha is in a more compact way is going to be given by that. And then we have the next one, which is B of alpha. This is an annihilation operator. So that means that if we are above the Fermi level, then we destroy a particle in a state alpha. So we would have, this is for alpha larger than F. And then we have an A alpha dagger for alpha less than F. So that means that we actually do create a state. So B of alpha destroys a hole, which is the same as filling a particle in that state which was vacant. Okay, you see the language which we're dealing with? That's it's a little bit important just to keep this kind of way of thinking. So you can now say that when you look back at these specific states which we have, suppose we have the state alpha here, and then if I now create a hole, so the filled circles are states which are occupied by a particle. So this is 1, 2, 3, and then I have n minus 1 and n. So this B of alpha dagger, that creates a hole. If alpha is below the Fermi level. And that translates into, in the old machinery, that means that we are taking out a particle from that state. But we create a hole. Now later, so I said that this is just going to be an intermediate step because it becomes a little bit cumbersome because we have to keep in mind all these notations. Later, we're actually going to go back to the standard operators A, which we had before, but we're going to put labels on them to indicate that this is a whole state and this is a particle state. And then we can simplify the formalism. But you will see this in just a few moments here. So this is F, and then we have n plus 1, etc. So when I have this B of alpha acting, suppose now that alpha is here, and I act with B of alpha, that destroys a particle in state alpha, or it annihilates a particle in state alpha, if alpha is larger than the Fermi level. Now let's look at the operators which we have in this specific case here. So if we take the number operator, we can rewrite that in terms of these new operators. And the way we would do that, when we look at the sum over alpha, so alpha runs from 1 and in principle to infinity, but the sum is actually approximated with this maximum number of single particle states which we have. And we would have an A alpha. This is a number operator, which we saw last week. But this is going to be approximated, obviously, with a sum over alpha equal 1 up to some number n. And then we have an A alpha, where little n is a number of single particle states. Now, we can rewrite this in the following way. We have a sum over alpha larger than F. So we have the states above the Fermi level. So this means that we are just taking alpha equal to F plus 1. And then we are going up to this number n. And that is something we can rewrite like this. And then we have the next term, which is given by alpha less than the Fermi level. So this is just a rewrite of the sum, nothing special. Now we can introduce these new operators. And if we do that, we see then that if I have alpha larger than F, this is the same as a B alpha dagger of B alpha plus this operator alpha less than F, and then I have B alpha of B alpha dagger, like this. So I'm simply introducing the definition of the operators, which I have on the previous slide. I mean, this definition here and that definition which you see here. Now, what happens, however, if you think back to what we discussed yesterday, that all the operators, if we want to use Wick's generalized theorem, all the operators should be on what we call a normal ordered form. That means creation to the left and destruction to the right. So we would then like to rewrite the last term in a normal ordered form. So what that is going to give us when we use the anti-commutation rules is that we have this term plus B alpha of B alpha is given by a Kronecker delta. So we're going to reuse that one and just rewrite that term. in the following way. So if you now have a Kronecker delta here, this alpha runs up to the last single particle state, which is the same as the number of particles we have present in the system. So I can rewrite this one in the following way. So I can have it like alpha larger than F, and then I have my B alpha dagger, B alpha, but now I get a minus, and then I have my alpha less than F, but now I have normal order of the operator, and I have a B of alpha, but then I get a plus, and then I have a sum over alpha less than F, and now I'm just summing over the Kronecker deltas. So this runs over all the particles which we have. So this runs up to n particles. So the last term here is simply a number, n. Because the sum which we had, alpha less than F, is actually the same as alpha goes from 1 up to n. So this is just simply the number of particles which we have. So let's just test this now by calculating expectation values. And already at this level, you will see that we don't need to deal with the contractions with all the particles. So let's look at that. So if I calculate the phi with this operator n of phi 0, we should get the number of particles as we showed last week. So when I'm now setting this up, this means simply that we need to evaluate whether it's above or below the Fermi level of this of B of alpha or phi 0. Now, what I have defined is that this contraction here is automatically 0. Okay? So that means that the terms which you get from here are 0. And the only term which survives then is just this one. So this one looks like that, and this is due to the way we define the contraction, it has to be 0. And the same with this one. We have it in normal order form. And as soon as you're calculating an expectation value with a normal order product, if you remember back what we did in the general case when we had this one of A, alpha, of beta, etc., this is automatically equal to 0. So when we have a normal order operator, we don't need to do anything. In our previous life, when we had the other operators, we actually had to look at all the possible contractions, which are defined by the states you have here. And if you have 100 states, you needed to look at the 100 possible contractions. Now, on the other hand, you have a much more compact notation because you have redefined your vacuum. Remember that this one previously was simply given by U going from 0, and then an A alpha and AB, 0. And that's automatically 0. So now we have the same rule, but with a new vacuum state. And this is going to help us in setting up the calculations because this is just 0. And the only term which survives then is actually this one. And that's just a number. And I have assumed, and I should add that, that's an important assumption, is that I assume now that phi 0 is a normalized and orthogonal state. So that means that phi 0 with phi 0 is just equal to 1. So I have 1 times a number, n. And this is the result which we actually wanted. And you see how much simpler this calculation is compared to what you had before. So let's now introduce some definitions here. And if you now look at the states which we have, we can now define new states. So if I now define new states, what I could do now is to act with this operator beta, B or alpha, or B or beta, and we could act on the ground state again. But now I'm going to make an assumption that alpha is larger than the Fermi level, and beta is included in the Fermi level. So that means that when I'm performing this calculation, what I'm doing now, if you look at this from this perspective of the single particle orbits, I am picking a state beta here. And here I have the remaining states up to the Fermi level, 1, 2, 3. There is a state beta, which I'm picking, and I'm destroying that. So that means that I'm having a vacancy here. These are filled. But then, if I look at the action of this specific operator, which you have here, this B of alpha, if we now have alpha as a specific state here, what I'm actually doing now is that I'm creating a particle which lives in this state alpha. So I am creating a whole state, and I'm creating a particle state. So no particles or states above the Fermi level. So this is something which we are going to call a one particle, one whole state. This is the notation which we will be using throughout the semester. So this is a one particle, one whole state. It's just a way to organize the states in terms of this type of excitations. So you would think of this as an excitation from the reference state, because you excite one particle from a state below the Fermi level to above the Fermi level. And we would typically label this one in the following way. So this is going to be given by a beta, which has been taken out. So the beta is a subscript, and then the particle state here is a superscript. So this is a kind of labeling which I'm going to use now throughout the semester. This is a particle whole, one particle, one whole state. Now, remember now again that you can organize the sequence of your possible configurations as you want. So I could have said that instead of looking at this in terms of one particle, one whole states, I could just simply look at all the possible permutations of these particles I have, n particles in this n. So the total number of states which we have is given by this binomial factor here, which is given by n of n minus n factorial, and then n factorial. And normally you have n larger or equal than n. This is a possible number of configurations which you can make. This means that I can now make a configuration where I have one particle, one whole excitation. And if this little n, which you have here, is an infinite number, which it should be, but we are truncating it, you would have an infinity of one particle, one whole states. But the number of one particle, one whole states which we have will obviously be then limited by where we put the cutoff on n. So this is just one way of representing the states. And now you see what follows naturally. If I now act with two creation operators and two annihilation operators, I will be creating a two particle, two whole state, and so on. And this is just a way to label the states. But the thing which is going to be nice for us is, since we have an interaction which is only at most of a two-body type, the interaction will mainly produce excitations of this type, like a two-particle, two-hole excitation. You can be in a one-particle, one-hole state, and if you perform a two-particle, two-hole excitation, you can get into a three-particle, three-hole state. If you have a two-particle, two-hole state you are in, you can create a four-particle, two-hole state with a two-body interaction, and so on. So this is going to give us a very compact way of setting up the system we deal with, but it's also going to allow us to make a kind of intuitive, how to say, definitions and intuitive understanding of what the different types of excitation mean. So it gives us a language which is very powerful when we want to develop an intuition about physical processes. So you see now immediately you can make a, if you have a B alpha and a B beta here, and a B gamma and a B delta, and where alpha and beta are larger than the Fermi level, and gamma and delta are below the Fermi level, that means that we have some selected states here there is a gamma here, and there is a delta here. And then we go up to the Fermi level. So we have F here, this is the last one. And then we are creating a hole here. These guys are still filled. And then we promote these up to some specific state alpha here. So suddenly we have filled that one. And then we have a state beta here. And then we have the other set of states which we can set up. And this is something which we would label as a two-particle, two-hole state. And we are going to use a notation where we now keep the subscripts as whole states. We would have a gamma delta, and then we have alpha beta. Later, I'm going to replace Greeks with the Romans, Roman letters. Just a joke from my side, Greeks and Romans. Okay, so this is just a way by which we now are going to rewrite the states. That means also that the state, like the one we discussed in the beginning, this alpha here, this is a one particle state. So it means I have added a particle to my reference state. And when I write this, alpha here, this is a one whole state. It means I have removed a particle in a state below the Fermi level. Okay, so these are just definitions, but now let's try to run some calculations here. So let's see what happens if I now move away from this number operator. So let's look at the one-body operator in this new formalism. So we have a sum here over alpha beta, and then we have the matrix elements, H0 of beta, and then I have A alpha. This is what we saw previously. And this is something I can now rewrite in terms of alpha and beta being larger than the Fermi level. So I would then have alpha, H0 of beta. And in this specific case, I'm now going to replace it with a B of alpha dagger and B of beta. I'm just using the definition of these new operators. Then I have a new sum where I assume that alpha is larger than F and beta is smaller than F. I still have this matrix element, alpha, this integral actually. And now this is going to give me a new operator, which is going to look like beta alpha and B of beta dagger. Then I have plus a new one, which is going to be given by alpha less than F and beta larger than F. And I still have this here of H0 of beta. But now this is going to look like beta of alpha and beta of beta here. So let me just bring up, I just need to find my small notes here. Where did I have it? Yeah. And then I have the final one where both of them, alpha and beta, are below F. So then I have alpha of H0 beta. And this is going to give me the following term. And then I have a B of alpha of B of beta. Now, the last term is not in a normal ordered form. I can also manipulate the two intermediate terms, the second and the third term. I can rewrite this one now, so everything is in normal ordered form. And I can also, for the last term, which is the third term, I can just interchange here alpha with beta, because these are just dummy variables, right? I mean, you can call them whatever you want. So I just interchange alpha and beta. And then what I would have then is that I can bring together these two summations, because then they're going to look the same. But then I would have different terms. And then in this final term, I'm going to rewrite this in a normal order form, and that introduces a Kronecker delta. which requires that alpha is equal to beta. So I'm going now to rewrite it. So this is something I can rewrite as an alpha or beta larger than f. And I have this integral, alpha h0 or beta, and then a alpha dagger, a beta. And then I have plus, and now I'm just going to write this in terms of a sum alpha over larger than beta f, and this one. And then I have my terms, because now I have to be a little bit careful. So I have an alpha of h0 of beta, and this contains b of alpha, b of beta, plus a term where I now have changed these two guys, and I have a b of beta, a b of alpha, and then I have a new term, which is going to be given simply by the Kronecker delta. So I have an alpha, and this is for alpha less or equal than f, and this contains just the Kronecker delta, which now simply reduces to this matrix element here, or this integral. Because what I did, I took this b of alpha, or b of beta, I want this in normal ordered form, and that's the same as delta alpha beta minus b beta, and then I have dagger and b alpha. So there is a new term here, minus, and then I have this sum over alpha and beta less than the Fermi level. There's going to be a matrix element here, which goes like alpha of h0 of beta, but this is now multiplied with b beta times b alpha. Now comes a very interesting thing here. If I calculate the vacuum to vacuum expectation value, which term is going to survive here? There's actually only one term which will survive. So if I calculate this now, phi 0 with h0 and phi 0. So keep in mind now that you have a contraction. Oh, sorry, this should be, I did something wrong here. This should be B, sorry. So just keep in mind, as a small hint, that these contractions with a new vacuum now, this contraction is equal to this contraction, and it's equal to this contraction, dagger, dagger, and they are exactly equal to 0. So if you now look at the operators which we have, you see that you have one, all the operators are normal ordered. You have here, this is normal ordered, this is normal ordered, and this one is normal ordered. So what are these going to give us as expectation values in here?
0.
0. And the only term which survives is this one, which is a scalar, right? This is just a number. We're just summing up. And then you see now that we get back the result which we had previously, just the sum over single particle states. So this term here is now simply going to be equal to the sum over alphas less than 0. And this is given by this integral h0. And if these alphas are eigenstates of h0, this is simply going to be alpha less than f and a sum over epsilon alpha. This is what we had before. So we are getting back what we want to have. Next week, we are going to make this even more compact. And the way we are going to do it is actually not to use these operators B, but we are going to go back to the normal operators which we had, but we are going to put subscripts on them, which indicates that this is now a particle state and this is a whole state. So I'm going to give you a small exercise before we stop today. And you can actually calculate immediately this contribution. So if I take now a Slater determinant where I have a particle whole state, a one particle, one whole state. So I have my state gamma here, and I have a state delta, and I want to calculate this expectation value here. what you're going to see, so I'm just going to give you the answer. This is going to be given by the single particle energy delta minus, so that's a particle energy, minus the single particle energy gamma, plus the reference energy. So which is given by the sum over alpha less than f of epsilon alpha. And then we have assumed that H acting on a state gamma is given by epsilon gamma times gamma. So we're assuming that these are eigenstates of the operator H0, which is a very common assumption as we discussed in the beginning, because that allows us to define a computational basis. So this is where we will start next week. And next week, we will also bring up the two-body operator. And then we are going to have a formalism, which we will elaborate on, which is going to be called the particle Hall formalism. And we are going to use that one next week to start with the first many-body method, which is going to be full configuration interaction theory, because then we are going to label all the configurations in terms of the reference state, the vacuum state, and particle Hall excitations. So that is just a way to relabel all your possible ways, configurations, in which you can distribute n, uppercase N particles in little n single particle states. And that's going to give us a compact way by which we can interpret excitations of given particle systems. And this Lipkin model exercise, which we have this week, I'm not expecting that you guys will be able to finish it this week, because we will keep going on with that one next week as well. And I thought of using that as an input to the first midterm. So many of the things we do now will be pretty useful for the midterm as well, which I thought of focusing on this Lipkin model, because it gives us a way to gain a useful understanding and develop our own insights about these different types of correlations without bringing in a complicated physical system. So as soon as you deal with atoms and molecules, you also have the complications of having to define the integrals and the single particle basis, etc., etc. Whereas with this Lipkin model, the interaction matrix elements are just constants. And the only thing we need to deal with then are just the type of excitations which we create. So my hope is that this allows us to, it did for me, to develop a kind of deeper insight about what we are doing and what the different methods mean. Any questions before we stop and make everything ready for the weekend?